doing internal loads and beams. Um, and the idea is based on the superposition principle, and that's a pretty common thing when you have small, well, in our case, we're talking about small deformations. But anytime you have small perturbations from some sort of reference position, that's when the superposition principle can come up. So it's such a cool name for such a simple thing. Um, and the idea is just that in for our case, and by that I mean, I guess the only thing that matters in this case for us is the fact that the deformations are small. But the stress tensor total is equal to, and this is in a beam, it's equal to the stress tensor due to tension plus the stress tensor due to bending moment plus the stress tensor due to the shear force plus the stress tensor due to the torque. Um, and when I talk about adding these stress tensors, they add the same way that vectors do, just element by element. So for example, if you have stress tensor 5, 0, 2, 0, 1, 0, 2, 0, -3, and you add that to 0, 5, 2, 5, 0, -4, 2, -4, 1. You just add them up element by element. So 5 plus 0 is 5, 0 plus 5 is 5, 2 plus 2 is 4, 5 plus 0 is 5, 1 plus 0 is 1, 0 plus -4 is -4, 2 plus 2 is 4, 0 minus 4 is -4, and then -2. Well, no. So I was just going to say that. I made those two symmetrical, and notice that if the two you're adding are symmetrical, the other one has to come out that way. So you never have to worry about adding stress tensors and they come out as something that can't be a stress tensor. And the reason this works is basically like, I mean, you can imagine if you bend something really sharply, bend it all the way down to a very noticeable angle, and then you applied tension to it, those loading patterns are going to react in some unpredictable way. But if all of these things are very close to their original configuration, because we're talking about very small deformations, then you have to worry about that a lot less. And those things, you get good accuracy by just calculating independently those loads. First think about a bar that's in pure tension, calculate the stress tensor. Now think about a bar that's in pure bending moment, calculate the stress tensor. So that's what we're going to do, add them all together at the end. And the general idea is for each type of stress, the stress tensor will depend on the internal load at the desired point. So all the stuff we just went through for internal loads is going to be the starting point for the stress calculations. All right, well, we're going to start with the easiest case. So stresses due to tension and compression. And we're going to use the coordinate system that we've used in all of our internal loads calculations, where the x-axis is along the length of the beam, the y-axis is up, and the z-axis is out towards us. And at any point in the beam, that has an internal load, or an internal tension T, the normal stress in the x direction is equal to T over A, where A is the cross-sectional area at that point. Okay, so this doesn't say anything about where on the cross-section you are, and that's because over the whole cross-section, the stress is the same. So it doesn't matter if you're near the top of the beam or the middle of the beam or whatever. All that matters is the x position. So let's do an example. Let's say we have a beam that when we figure out the external loads, there's a 8,000 Newton force at the left end. At the middle, there's a 2,000 Newton force. And then at the end, there's a 6,000 Newton force. And the cross-sectional area, let's say it's constant over the whole thing at 0.001. Yeah, meters squared. So what are the stresses as functions of x? You know, how is the stress in the beam going to change as you go along the length? Well, we're always going to start by calculating the internal loads. So how many cuts do we have to make? Normally we'd have to calculate the external loads, but they're already given. 2 cuts, yep. So the first cut is going to be for x between, I didn't say how long this was. Let's say 0.5 meter each. Okay, so the first cut is from 0 to 0.5. So we'll take some representative cut. We have the 8,000 Newton force at the left end. but we haven't gotten to the 2,000 Newton force yet. So the only other loads are the tension, the shear force, bending moment, all that stuff's going to be zero. All we have is forces along the x-axis here, so I'm just going to write it like this. But if you wanted to go through the full calculation, you could calculate shear force is zero, moment zero, fancy T is zero. And then Newton's second law says negative 8,000, 0 plus T0 is equal to zeros. So we got that T is equal to positive 8,000 for every x value between 0 and 0.5. And that's a positive value, so that means that that whole piece is in tension. And now cut 2 is between 0.5 and 1. So now we have the 8,000 here. And now somewhere else we have the 2,000 going the other way. And the tension. And so Newton's second law says negative 8,000, 0 plus positive 2,000, 0 plus T0 is equal to zeros. And so T is equal to 6,000. So now that we have the internal loads, for any x values between 0 and 0.5, sigma xx is equal to positive 8,000 divided by 0.001. And so that's 8.0 times 10 to the 6 pascals. And if you wanted to give the full stress tensor, that's the XX element. So that's 8.0, 0, 0, zeros everywhere else, if you write it in megapascals. And notice, if you think about what that means, a positive, so a positive tension as an internal load means the thing's in tension. A negative value means compression. And now think about the stress element, and it means the same thing. So we're going to use the sign that we get for the internal loads to calculate that stress, and it works out. The meaning makes sense. I'll write that in a second. And on the other half, for x in the range from 0.5 to 1, the XX stress is positive 6,000 divided by 0.001, and that's 6.0 times 10 to the 6 pascals. And so the stress tensor on that half, for any point on that half, is 6.0, zeros everywhere else. In megapascals. So now what that says is, in this case, if you're trying to figure out where you're concerned about this bar breaking or deforming permanently or something like that, the half that you know, the place that you want to investigate is the left half of this beam. Okay, that's where the stresses are higher, and so that's what you're worried about. If it's good on the left half, then it's good on the right half too. Okay. Well, if the right half had a different cross-sectional area, then, you know, say that the cross-sectional area got smaller on the right half of the beam, then it's possible that even though the internal loads are bigger on the left half, the stresses when you divide by the cross-sectional area would be bigger on the right half. So this is the best indicator of how concerned you are about fracture or whatever. Okay, so I want you to notice one thing. Trust the signs from the internal tension. That's going to be true for every one of these calculations, I think. Maybe not torsion now that I think about it. But I'm going to make a point out of it every time that it's a thing. Okay, so we just, whether it's positive or negative coming from the internal loads, we use that signed value to calculate the stress. Yes? Well, we don't know that it's going to break at all. We just know that, so there are different kinds of criteria you use for different types of materials to determine whether you think it's going to break. For very brittle materials, we'd mostly just want to calculate the maximum shear stress. We use this value to calculate the maximum shear stress in this environment. And then we go to some table. And for our material, compare to the maximum shear stress you expect for that material. And if our value is higher, then we need to do something, either make the cross-sectional area bigger or reduce the load somehow. For materials that can stretch more before they break, more ductile materials, metals, we would want to calculate the strain energy, which is a combination of the stress and the strain. We're not going to talk about those kind of things, but it's not like the calculations are hard. But it's more just not really a part of this class because the criteria you use are so different for different types of materials. But anyways, so we would take our loads, calculate our strains, figure out whether we think under those loads this thing is going to break or not. If it looks like it's safe, then we're good. If our strain energy value or our maximum shear stress or whatever criteria is bigger than the maximum that material can sustain, we have to do something about it. But so a lot of times we're just going to be looking, we're going to want to just identify the points where we're most concerned about the material, where the loads are the biggest, the stresses are the biggest. And then if it's fine there, then we don't care about it at all.